Here's a probability question. You have two bags, and the first bag has 5 red and 3 blue. The second bag has 2 reds and 14 blue. And the question is, if you randomly pick the bag, like switch things around, randomly pick the bag, and you picked one marble out, what's the probability of getting a red marble? It's not so easy to approach it just using probability formulas. So rather than doing it that way, let's first try to find the answer by just imagining doing this procedure like many, many times. And one of the ways you can think is like there are 8 marbles total. This says 60 marbles total, so there's 24 marbles in total. Since you have 2 bags, let's say we did this trial 48 times. Yeah, and then assume that all the outcomes come out exactly according to the probability and see how many of those 48 times we get the red marbles. Sounds like a plan, right? So let's do that. If I repeated this procedure 48 times, 24 of them will be picking this one. 24 of them will be picking this one. Again, we're assuming that we're doing everything according to the probability. Oh, wait, just a minute. This is 16, and 24 doesn't get divided into 16 cases, so that's not good. I think we should do 96. Okay, so let's say 96. So if you did 96 times, then each of these will be 48 times, right? This bag will be picked 48 times. Out of these 48, that's the expected value of getting the reds will be, it's 5 out of 8 times, right? So that's going to be 6 times 5, that's going to be 30. And for this one, 48 times, that's there are total 16 marbles, and among them there are 2 red marbles. And if you compute that, that's 3, so that's 6. So out of 96 trials, 36 cases will give you red marbles. This is assuming everything is done according, it comes out as probability. Yeah. And if you reduce this is 12 times 3, so and then this is 8 times 12, so 12 cancels, and 3 out of 8 is the probability. Okay. All right, so the answer to the first question is 3 out of 8. Now, I will go over a different method to get the same result, but at least we know the answer is 3 out of 8. Okay. Now, here's an interesting second question, which is, what if you took these 2 bags and just put all the contents out into a single tray or something, and you randomly pick something? So blindfold a person, tell them to pick a marble. Now, would the probability of getting a red marble increase, decrease, or stay the same? Like, if you didn't think about this question for a long time, your first gut instinct is like, why would it change? This should be staying the same, right? But then maybe it has something to do with how you're doing things. So maybe this might change the probability. So let's go and see what's changed. So you mix these together, then there will be 7 red marbles. So if you pull them together, then you have 7 red marbles and 17 blue marbles. And that means that total out of 24, you have 7 out of 24 is the proportion of red marbles from the entire marbles. Okay? So in one way to say this is like the probability of choosing a red marble for the second case would be 7 out of 24. Another way to compare with the first way we were doing this is like, what if we did this trial 96 times? Then 96 divided by 24 gives you 3. So out of 90, if you multiply this by 96, then you get 21. So you can also say, if you did this trial with this situation 96 times, you're going to get 21 out of 96 to give you the red marbles. Okay. Now, what was this one? This was 36 out of 96, right? So you can see that since 3/8 is the same as 36 over 96, and 724 is same as 21 over 96, and if you compare those two, you see that indeed the probability decreased. So the answer is decreased. But then, can you come up with a rationale how that would happen? Why would it decrease? It's something that you should think about. You have a reason?
Yes, it is better. It's gotta be because you mix together.
So when you mix together, it's always decreases.
But the first bag you have a better chance of getting red.
So why does it decrease? Like in this situation, when you mix, you always decrease, or what's happening here? What's the rationale?
See.
So
I mean,
okay.
If you have a chance to pick either the one with a lower chance to get red, and you have a chance to go.
Yeah. So this is a bag with high chance.
Yeah.
And this is a bag with low chance. I mean, if let's say red marbles will give you $10 and blue marbles gives you nothing, and people all would want to get the red marble. So this is the bag it's a good bag, and this is a bad bag. Okay. So what?
So one has an advantage over the other if you want red, but if you combine them, then you get rid of that advantage, and now it's just like.
No, not exactly. It has something more. It's not just that. There's something else that you have to notice about those bags.
Because the low one has like so much more blue.
So many. No, not that.
Way more marbles.
Way more marbles. That's the key. It has more marbles. So think about this. If you pull them together, 1/3 of them will be from the high bag, and 2/3 will be from the low bag, because this guy has 16 marbles. This only has 8 marbles, right? So it's like if you pick random marble from here, would you have more chance of picking from the low one or the high one?
Or no, low one.
The low one. It's more representative. So if you pick something random, you're going to pick something from here.
Yeah.
But this one has a lower probability, so it's like so if the first one was like taking just the average of the two probabilities, so in fact, if you do 3/8 plus 2/16 and divide it by 2, I'm not so sure. All right. Yes. Okay. So you can think of the first one as the high bag is 5 out of 8, and second is 2 out of 16. And just first randomly choosing one is like taking the average of the two. So this is 1 out of 8, so it's 5 out of 8 plus 1 out of 8. Right? If you reduce 2 out of 16, that's 1 out of 8. So if you divide it by 2, you get 6 out of 8 divided by 2. So 6 divided by 2 gives you 3 out of 8. Right? So that's what it is. It's just the average of the two probabilities. That's what you're doing. But here, because you have much higher chance of ending up picking the lower one, it's like you're taking weighted average. You know how to do weighted average? Since this is twice represented than this, you multiply 2 to this one, and then you divide it by 3 because the frequency is 1 plus 2. Is that okay? Yeah. So if you do it this way, 2 and 16 cancels to give you 8. 5 plus 2 is 7, so you have 7 out of 8 divided by 3. And you can multiply 3 to 8, and that's 7 out of 24. Okay. So you have a weighted average of the two probabilities where this is twice weighted than this. That's why the probability will go down. So Here's another situation. If it was instead 10 red marbles and 6 blue here, but then 1 red marble and 7 blue here, now the probability is, again, this is 5/8 and this is 1/8, right? Yeah, same as before. 2 out of 16 is same as 1/8. So you might say, okay, if I pull this together, would I still get 7 out of 28? No, we don't. It'll be 11 out of 28, 24. 11 out, not 7 out of 24, because now it's the higher one is more represented. Yeah. Okay. So that's what's happening. But we need to approach this more systematically. So hopefully that analysis taught you what's going on. But see, the way you calculate probability is there's an end, there are stages. If you do something and then do something, then the probabilities multiply, right? But then if you have different cases, different cases, then you have to add. So here's how things go. You could have bag 1 and then get a red, or bag 2 and then get a red. Let's try to calculate each probabilities and see what we can do with it. So what's the probability of getting a bag 1? It's 50%, or 1/2, right? Probably getting bag 2 is also 1/2. And then if you pick bag 1, what's the probability of getting red? It's 5 out of 8, right? Okay. And then if you want to know the probability of this case, you multiply these two. So 1/2 times 5/8 is, so 1/2 times 5/8 gives you 5/16. And what that means is, if you do this, the probability of picking bag 1 and getting a red is 5 out of 16. Did that make sense?
Yes.
Yeah, probably getting bag 1 and then red is 5 out of 16. All right, now what about this one? If you pick bag 2, it'll be 2 out of 16, or if you reduce 2 out of 16, that's same as 1 out of 8. So 1/8 is what you get. And when you have probabilities in stages, you have to multiply, so that's going to give you 1/2 times 1/8, which is 1 out of 16. Okay? Now you have two different cases where, are there any overlaps between these two events? No, there aren't any, right? So when you have these two probability and we want just the probability of getting the R, you just have to add these two. And that gives you 5 out of 16 plus 1 out of 16, which is 6 out of 16. And that can be simplified to be 3 out of 8. Okay, on the other hand, this one is exactly what it says. You're mixed, so there is no two different cases of bags. There are just 24 marbles out there, and 7 of them are red. So it's actually simpler. This is just really basic math. If anyone was given this question without part A, and given this, nobody would hesitate at all. They're just going to say, oh, it's 7 out of 24, right? It's just that this one just gives you a confusing background story that it's hard to say something, but this is, of course, 7 red marbles out of 24. And of course, this is 9 out of 24, and since this is bigger than that, so the answer is this one is smaller. It's smaller probability. Okay. Now, however, we are going to rewrite what we just did in a better way. And to talk about that, we'll talk about conditional probability. So this question is an excellent introduction to conditional probability. where probability of A under B, this notation is probability of A if B happened. Okay? And we can say something like this. The total probability of red happening is same as probability of choosing bag 1. Oh, let's call x1 as choosing bag 1. If I just put number 1, then it's it's hard to understand what that 1 means. So we'll use x1 as the event where the bag number 1 is chosen. Okay, and then multiply that by probability of getting the red under the knowledge that you've chosen bag 1. Okay, and what is p of x1? That's 1/2, right? What is p of rx1? That's this 5/8. Because bag x1 has higher probability, this is going to be 5/8. Right? Okay. Plus, now probability of what? Bag number 2, and then what? Probability of r under
X2.
x2. Okay, that's what you have. And this thing that we computed is exactly what this formula is saying. It should be 1/2 times 5/8 plus 1/2 times 1/8. So you get a nice formula called Bayes' theorem. So if, I'll just write it here. So first version is P of A is equal to PB times P of A under B plus P of B complement times P of A B complement. What I wrote here is just a repackaging of this. See, if x1 is the event that you choose the first bag, then what's the event that you choose the second bag? It's complement of not choosing the first bag is same as choosing the second bag, right? So that's what B complement means. Okay, so this is the formula. If you have like a binary 2 cases, let's say there's some important second event that determines the outcome of the probability of the probability A. Okay, it's hard to just figure out probability A because there's something called B that determines the probability. In that case, you think about the probability when B does happen and multiply the probability of A happening under the condition that B happened, plus the probability of B not happening and probability of A happening under the condition that B did not happen. That's called Bayes' theorem. Now this has a more general case. So suppose. So that's number 1. Number 2. Suppose A, B, C are mutually exclusive events. So what that means is like A intersection B is nothing. you can't have any of the two things happening at the same time, okay? That's what mutually exclusive is. And P of A union B union C is 1. And this means that basically any event that happens belongs here. Okay. So in other words, the entire space of possible outcomes is divided into 3 different cases: A or B or C. Okay. That's the situation. See, over here I just had B or not B, right? So it's like this is a case when the situation is either something happening or something not happening. Either when X1 is the first bag is chosen or first bag is not chosen, which means the second bag is chosen. Okay, so that's this one. But what if it's divided into 3 cases? In that case, probability of a fourth event D is going to be probability that A happens, probability that D happens when A happens, plus probability that of B times probability of D happening when B happened, plus probability of C when and then probability of D happening when C happens. Is that okay? Yeah. And then you can see that this can be further done, like if you have like a E1 through En mutually exclusive events, and so these are mutually let me write this straight, mutually exclusive, and let's say E1 union through En, probability is everything, so this captures all the possibility, right? Then, by the way, there's something with some measure theory stuff that becomes a problem when these are. Okay, we'll only limit our discussion to when your independent events have positive probability. There's some continuous probabilities where you need further assumptions. Okay, but anyways, if you have this, then probability of A happening is same as probability of E1, or we'll just write it as sigma. Okay? There's a summation of probability of EK, probability of A under EK, with all possible K's, like K equals 1 through N. So that's the most general one, and these are called Bayes' theorem. Now, however, there's another thing that you should gain from here. So notice that this by itself has a meaning, because over here, when we just did this times this, right? What was 1/2? That was probability of getting the bag 1 times probability of getting red under the bag 1, and we got 5 out of 16. But that had a meaning. What was the meaning? This is when you have probability where you chose bag 1 and you got the R, right? Okay. And that means, in general, if you multiply PA or PB times PA under B, that gives you the probability of A and B happening at the same time. Okay? Now, you can do several different examples and see this is always true. And this is more exact than my previous comment where, if you select by stages, you have to multiply. The correct way to say it is that if you want to say something happened and, remember this intersection is in set theory, it's and, right? What is this? This is a set of things that belong to both A and B. And is the important word here. So if you want something, the probability of an event where the first bag is chosen and the red is chosen, right? Then you have to multiply the first probability of getting the first bag times probability of getting the red, however, under the condition that, with the knowledge that the first bag is chosen, okay? That's how you get this. Okay, so the correct multiplication rule for probability has this thing in it, okay? Now, last comment. However, sometimes it's not so straightforward to see what the conditional probability is. In that case, we can also think of this as the definition of the conditional probability. So my last comment here is that you can solve this for P and B and say this is the definition. P of A under B is probability of A and B happening at the same time divided by P of B. Okay, so this is going to be a very important identity that we're going to investigate further next time.